Alright, in this video we want to learn how to draw the graphs of what are called rational functions. And a rational function, rational is basically a fancy word for a fraction. So here's an example of a rational function. Let's suppose I had something like f of x equals, let's say 1 over x plus 2. Simple rational function. This right here is a ratio. It's a ratio of the number 1 to x plus 2, and it's called a rational function because of that, because of the variable in the denominator. Essentially, it's exactly like a fraction. The only difference is a fraction normally just has a number over a number. A rational function or a rational expression has not only numbers but also variables included. Alright, so what we're going to try to do is sketch the graph, and there are 6 main things to do, and I have kind of a summary version right here just to have as a guide as we go through these. First thing we want to do is anytime you have a rational function, you want to see if there's things that you can factor on the top and the bottom. And we've obviously factored before, so that's not going to be a new thing. So we'll factor anything that can be factored. It's useful for us to know what the x-intercepts are and what the y-intercepts are, because when we're graphing, if I know that the x-intercept is right here, well, that's going to help me know where to draw my graph. If I know that the y-intercept is right here, now I kind of can connect the dots like that. So we want to know what the intercepts are, and we'll show you how to do that. Okay, then we want to find what are called asymptotes, and there are 2 types. There are vertical asymptotes and horizontal asymptotes. An asymptote, and this will be clearer when we actually do the example, but the asymptote is basically a line that the graph gets really, really close to, but it never actually touches. That's exactly what we mean by asymptote. So for example, if you had a graph, let's say that looked like this, and let's say I was kind of drawing the graph, you can see up here that this thing kind of levels off. It gets really close to that blue line, but it never touches. And that, by the way, that would be an example of a horizontal asymptote, because this blue line is a horizontal line. Okay, we'll also see what vertical asymptotes look like. Okay, then we want to see if there are any holes in the graph, and I'll show you how to do that. And then the last thing is once we have all that stuff, we can draw the graph. Okay, so there are 3 different cases that can result. These are cases based on what the graph's going to look like. So case 1, which we'll do right now, is what happens when the degree of the denominator, so here's what we mean by that. This down here, that's x squared, and the degree of the numerator, the largest degree, is x to the first up here. So we can see the denominator has an x to the second power, the numerator has an x to the first, and that is one case that we'll talk about. We'll talk about the other 2 cases shortly, when the degrees are the same, and then what happens when the denominator is not larger but smaller. Alright, so let's go through our steps here. So the first step is we want to factor. If we look at the top looks like a -2 can come out of that, because -2 comes out of -2x. It also comes out of -4. So if we divide -2x by -2, we'd have x. If we divide the -4 by -2, we'd have +2. Okay, then the bottom we can factor as well. So the bottom, we're looking for numbers that multiply to +8 and add to +6. And the numbers that do that are x plus 4 times x plus 2. So we're done with that part. We've now factored it. Okay, the next thing we want to do is find the intercepts. So we'll start with the x-intercepts. Okay, and the x-intercepts are basically, on a graph, the x-intercept is where it hits the x-axis. And if you look at this x-axis right here that I'm tracing in blue, question that I want you to ask yourself is, what is y equal all along the x-axis? Not what is x equal, what is y equal? And the answer is y is equal to 0 everywhere on that blue line. Notice that at this point right here, right at the origin, y is 0. I haven't moved up or down. If I'm moving along the blue line, I haven't changed my y position. I've only changed the x. So y equals 0 everywhere on that line. So we can find the x-intercepts by setting y equal to 0. So now if you look at this equation right here, I'm just going to rewrite it. If you look at this equation and we set it equal to 0, the question to ask yourself is, how could this thing actually equal 0? How is that even possible? Okay, and the answer is the only way to make this 0 is if this right here were equal 0. There's no way to make -2 0. And I also can't have these being 0. These cannot be 0. They can't equal 0. Why can't they equal 0? Because in that case you'd be dividing, you'd have a fraction where the bottom of the fraction was equal to 0. Okay, so for example, if let's suppose the top, we plugged in some number, we got 8, and then we plugged in, like, let's say -4 right here. If we plugged in -4, the bottom would be -4 plus 4 is 0 times, and we don't even care what that other one is, 0 times anything is 0. If you took this and put this in a calculator, you can't do it. It gives you an error. It's not gonna work. So we can never have the bottom of the fraction equaling 0. Okay, so the point is the only way that this equation equals 0, which is what we're trying to find right now because the x-intercepts occur when that happens. The only way this could equal 0 is if the top equals 0, and the only part of the top that can be 0 is this part. So when we solve this, it looks like x equals -2. That right there is the x-intercept. So I'm going to put a point right there at -2. Okay. Next thing we want to do, so we found the x-intercepts. The next thing we want to do is to find the y-intercepts. Okay, and the y-intercepts, the x-intercepts occur when y equals 0. The y-intercepts occur when x equals 0. So I'm going to take this exact equation that we have, the original equation, but wherever I see an x, I'm now going to plug in a 0 because that is where the intercept occurs, the y-intercept that is. Okay, so the top was x plus 2, now it's going to be 0 plus 2. The bottom will be 0 plus 4, 0 plus 2. Okay, this top thing, 0 plus 2 is 2, so -2 times 2 is -4. And the bottom is going to be 4 times 2, which is 8. And -4 over 8 simplifies to -1/2. Again, where did that come from? It came from taking this equation and plugging in 0 wherever I saw an x. And we get the point x equals 0, y equals -1/2. That's going to be on our graph. So let's make sure we graph that. So 0, -1/2 is going to put us right there. Okay, so we have at least 2 points, and we found our intercepts. Okay, now the asymptotes. There are two types of asymptotes. There's a vertical asymptote and there's a horizontal asymptote, and then also there's something called a hole. So here's the difference between a hole and an asymptote. For both of these, vertical asymptotes and holes, so both of these, I'm just going to write this down, vertical asymptotes and holes, they both occur when the denominator is equal to 0. Okay, and the denominator means the bottom of the fraction. So when the denominator equals 0, vertical asymptotes and holes both occur. The question is, what's the difference? And here's the difference. Holes occur if you can cancel something on the top and the bottom. If you can cancel a common factor from the top and the bottom. That's when a hole would occur. And a vertical asymptote would occur, I'm just going to abbreviate that VA. Vertical asymptote occurs if you can't cancel something from the bottom. Okay, so what does that mean in the example that we're doing right now? So let's take a look at this right here. This is our function that we're trying to graph. So if you look at the top and the bottom, what are we able to cancel? And the answer is we're able to cancel right here. We're able to cancel an x plus 2. Those will cancel. So we said right here, if you can cancel a common factor, we can cancel the x plus 2. If we can cancel that, that means there's going to be a hole at the x value that would make the bottom 0. And if you look at x plus 2, what would make x plus 2 equals 0? We solve that right here. X equals -2 would cause that to be 0. Okay. So even though we filled in that x-intercept right there, and I filled it in with a solid line, I'm now going to go back and erase that. And I'm going to replace that with a hole right at that point, because there will literally be, if you were to graph this on a graphing calculator software, and I'll show you how to do that in just a sec, if you were to graph that, you would end up getting just a hole at that point in the graph if you zoomed in. Okay, and like I said, I'll try to get a picture of that for you. So we're going to have this hole at -2, and actually I don't want to fill this in yet because we don't know exactly. We know it's going to be x equals -2. We don't know where the y is going to be. So I'll show you that in just a sec. Okay, so now that leaves us with x plus 4. Well, x plus 4 is not going to create a hole because we can't cancel it. There's no x plus 4 on the top of this fraction. So that leads us to this, the vertical asymptote. If you can't cancel, we cannot cancel the x plus 4. If you can't cancel that, you see what it makes it equal 0. X equals -4 would make that parentheses right here equals 0. So x equals -4, we're going to have literally this vertical line here. This is called a vertical asymptote. And the graph will get very close to that line, but it will never actually reach it. And I will show you why in just a sec. Okay, so that's our single vertical asymptote. The other thing to keep in mind is however many vertical asymptotes you have, that means you're going to have one extra region of the graph. So what do I mean by that? If you have one vertical asymptote, that means you're going to have 2 regions of the graph. If you had 2 vertical asymptotes, you would have 3 regions. If you had 3 vertical asymptotes, you would have 4 regions, and so on. Okay, so we took care of the vertical asymptote. So the VAs are taken care of, the hole is taken care of, and actually let's finish that right now. So I said -2 would normally have been an x-intercept, but in this case it's not. There actually are no x-intercepts. Why are there no x-intercepts? Because when we plug in negative 2, this causes a problem on the bottom right there. We would get 0 in that case. So because we were able to cancel those x plus 2's, we will have a hole at negative 2, but it's not going to be an x-intercept. If we were to plug in negative 2 to this equation right here, we'd have, let's do that right here. Let me move it aside so we can kind of make a table of values right here. So if we were to plug in negative 2 to this function, we'd have negative 2. Remember that the x plus 2's have now canceled each other out. If we plug in negative 2 right here, we'd have negative 2 over negative 2 plus 4 is 2. So we have negative 2 over 2, which is negative 1. So what that means is at x equals negative 2, y equals negative 1, that would normally be a point on the graph, but at that point there's literally going to be a hole in the graph. So negative 2, negative 1 is right here, and I'm just going to draw an empty, kind of like a hole right there. So you can see it's not going to go through there. All right, so step 3 is usually the longest here, finding the asymptotes in the holes. We found the vertical asymptote in the hole. The other type of asymptote is called a horizontal asymptote. And the reason I call this case 1 is because the degree of the denominator is larger than the degree of the numerator. So here's what that means. Here's what a horizontal asymptote is. Okay, a horizontal asymptote occurs as x goes to either positive or negative infinity. Okay, it occurs as the graph, so this is how you would say that, as x travels, the arrow means travels to positive infinity, so that means really big positive numbers, and also as x goes to negative infinity. That's what this symbol means. The arrow means x goes to, and then that little sideways 8 symbol is the infinity symbol. So let's take a look at this graph. So we have f of x, and by the way, f of x is interchangeable with the letter y, so I'll just write a y above that. F of x equals this right here. This is our original equation. And we are now asking what's going to happen to this graph as x travels to infinity. So here's what would happen. You'd have negative 2 times infinity minus 4 over infinity squared plus 6 times infinity plus 8. Now here's the thing to think about. As x is getting infinitely large, what's going to happen is this minus 4, that doesn't even matter. Infinity is so much bigger than minus 4, we don't even care about that. Same thing down here. The 8 is so much smaller than infinity, and also the infinity squared is way bigger than just regular infinity, so we don't even need to consider those other two terms. The only things we're considering are the largest degree for all of these. So the largest degree of the denominator, the largest degree of the numerator. So this whole thing really becomes like negative 2 infinity over infinity squared. The infinity squared is going to dominate everything else in the denominator, and the 2 infinity, or the negative 2 infinity, is going to dominate everything up there. Okay, so even though you can't really treat infinity like a number, for the purposes of understanding this, we're going to treat it that way. Pretend that this was negative 2x over x squared. Well, of course, you would be able to cancel that x there and one of those x's. You'd have negative 2 over x. Same thing right here. You can cancel, almost like cancel an infinity and one of those. You'd have negative 2 over infinity. Okay, so here's the question. What would happen if you took a number like negative 2 and you divide it by infinity, or you divide it by a massively large number? So if we want to see what would happen with that, imagine, let's just take bigger and bigger numbers and see what happens to them as we divide them by infinity. Okay, so we'll divide negative 2, we'll stick with that number negative 2, we'll divide it by 1, and we'll divide it by bigger and bigger numbers, so by 10, by 100, by 1,000, you'll be able to see pretty quick what happens. So negative 2 divided by 1 is negative 2, negative 2 divided by 10 is negative 0.2, this one is negative 0.02, this is negative 0.002. So you can probably see as we're going this way, as x, as the bottom is getting larger and larger and larger, what is happening here, this number is getting smaller and smaller. That basically means that this function, f of x, is going to 0. And that number, 0, that is what we mean by the horizontal asymptote. What does this function get really close to as x gets enormously large? It gets close to 0. It gets close to y equals 0. So our horizontal asymptote right here is this. I was about to try to draw a straight line. That was not a very good straight line right there. This horizontal asymptote right here is going to be y equals 0. That's our asymptote. And that's why I call this a case 1. That will always be true. HA means horizontal asymptote. That will always be true. The asymptote will always be 0 in a case 1 example. Case 1 meaning this. The degree of the denominator, which right here is x squared, is larger, I mean to say, than the degree of the numerator. So x squared is larger than x. the asymptote will always be 0. Why? Because this is like infinity squared on the bottom and infinity on the top. The infinity squared basically wins out right there. So infinity squared is much larger. That means you're going to take a number on the top over a much, much larger number, over a huge number, and that will put you close to 0. All right, so now we have everything. The last thing we need to do is draw the graph. So right now this doesn't look like a great graph, so the way that we can fill this out is just by making a pretty simple table of values, which we'll do right here. And what kind of values do we want to go in here? So our original function is negative 2x minus 4 over this right here. And all that we want to do, we have two regions of the graph, so I'm going to pick 2 points in each region. 2 points to the left of that asymptote, negative 4. So let's do negative 5 and negative 6. 2 points to the right. And actually, we don't even need to plot anything to the right because we now know what it looks like. Notice that these two red points are on the graph. The only way that I can connect them is with that line. And then this right here, it could either go up, it could go up here, or it could go down here. So I'm just going to pick a single point that is to the left of negative 2, and that will tell us whether it's going up or down. Okay, so we need a point to the left of negative 2. Why negative 2? Because negative 2 is right there at the hole. So let's pick negative 3. And then I already know that that y equals 0 is an asymptote. So that what this blue line is going to do is get really super close to that, but it will never actually touch. Okay, so all I need is a point, and I'm going to take each of these x values and plug them in. So if we plug in negative 5, negative 2 times negative 5 is 10 minus 4. And if you plug in negative 5 to the bottom, that's, what's that? 25 minus 30 is negative 5 plus 8 is 3. So this becomes 10 minus 4 is 6 over 3. That equals 2. So negative 5, positive 2 is on this graph. That puts us right here. And then if we plug in negative 6, it will be negative 2 times negative 6 is 12 minus 4, which equals 8. And the bottom becomes 36 minus 36 plus 8. So 8 over 8, that equals 1. So negative 6, 1 is right here. Now the only way that I could connect those two blue lines is right here. And then I know that that red line is a vertical asymptote. I know it has to go up because it's not going to suddenly change direction. Okay, similarly, I know that this blue line right here is going to kind of tail down. It's never going to actually touch that maroon colored y equals 0 line because it's an asymptote. And then our last one, negative 3, if we plug it into that equation, we'd have 6 minus 4 over, what's that going to be? 9 plus 8, 17 minus 18 is negative 1. So this is 2 over negative 1, which is negative 2. So we have the point negative 3, negative 2 puts us here. Now I know that, again, I can only connect them using that line, and it would have to go down towards that asymptote. It's not going to suddenly, swing up here somehow. So that's what the graph looks like. Quite a few steps, but I hope the idea made sense that in order to get a good picture, we need to do these 4 things that you see listed under summary. We need to factor, find the intercepts, asymptotes, and holes, and then draw the graph. And in the next video, I'll just show you what the picture looks like. And then we said that there are 3 cases. There's a case 1 right here. I'm going to show you what case 2 and case 3 look like as well.